Welcome to our next lecture in the series on condensed matter theory. In this lecture I want to talk about how to construct a local basis that we can use in a tight binding theory and how we can construct this with the use of Bloch's theorem. And what we have seen that in the previous lectures we have discussed the plane waves as a basis set with psi k of r is a wave e to the I k dot r, and for Coulomb potentials this is not a nice basis set as you have to deal with divergences in the potential, and this gives rise to divergent interactions between two basis functions. Now we can of course generate general bases. And we know that our plane wave basis is a complete basis set, so we can write our general basis as a sum over all basis functions, some complex prefactor, such that the norm square of all the prefactors is equal to 1. It's a unitary transformation. So any set of alphas that would define a unitary transformation, going from states labeled by the wave vector k to a set of states labeled by the quantum number tau, would be a valid transformation and gives you an equal description, mathematically at least, of the physics that you're after, but it might be a much more optimized set of basis sets of basis states that allow you to see the physics that goes on much clearer and easier. And that's what we're after. So which set do I choose here? We know that the eigenstates in a periodic potential are given by Bloch waves. So our eigenstates can be labeled by crystal momentum and an index tau. Note that I use the label tau just as a general quantum number where I do not specify the specifics of that quantum number. So here it can be anything, it can be atomic wave functions, it can be wave functions, it can be any basis set that you like. And the same here, and this tau does not necessarily label the same set of states as this one. We have a countable set of states and we just index them with the quantum number tau. Well, Bloch tells me that this is an e to the I kr times some periodic wave function in k and r, such that capital U of k and r of r plus r is equal to, it's periodic in the lattice, that is Bloch. So if I choose my basis set such that I find my wave functions to be given by a plane wave e to the ikr times a periodic function, then I know that I have diagonalized my Hamiltonian already in the crystal momentum. So as a basis set, I want to choose wave functions psi k and r of the form e to the I k dot r, and it's now the small u kr tau of r. And again, this is a periodic function where u k tau of r plus r is u k tau of r. We can express these, the eigenstates, as linear combinations of functions of our basis set, and we know that the eigenfunctions now will be a sum But we don't have to sum over the crystal momenta because crystal momenta is the same for each of them, and we only have to sum over the index tau. There's no vector here. Alpha k e tau as index psi k e of r. And we know we're Bloch diagonal in the crystal momentum. Or in other words, we can relate the periodic function of the eigenstate to the periodic functions of our basis u kappa tau of r, uk of tau of r is equal to the sum over I alpha k I tau u k I of r. And again, we only sum here over I and not over the crystal momentum, because we know that we're already diagonal in crystal momentum. And we know we have a symmetry in our system. If you translate your lattice by a reciprocal lattice vector, your wave function picks up some phase. The translation commutes with the Hamiltonian, and that phase is e to the I kr. That means that there is a crystal momentum that is a converged quantity of your system. So let's use it to define our basis set, such that they already do not change, conserve crystal momentum. So the question is, how do we choose this small u? So how do we choose u kappa tau of r? And in principle, we are free to choose any orthonormal set of periodic functions. And we can start, in order to make this set of periodic functions, by choosing a local function. And a local function, in principle, is any function that after some range exponentially decays and is normalized. And we can choose the atomic functions for this. And as we will show later in this series of lectures, is that we're going to modify the atomic function slightly as a convenient basis set. But we can think of them as the atomic wave functions. When we choose the atomic wave functions, then for sure you've already solved all the divergent problems close to the nucleus where your atom sits, because there you have the exact solution. So we no longer have to worry about all those divergences. Now from these local functions, we can build a periodic function. And our basis set is now going to be a sum over all lattice vectors normalized to the number of lattice vectors, the volume, and then e to the I k dot r, and then our local function shifted by the lattice vector. So this is the local basis function centered around capital R. V is the volume of a large box. And we put that volume in units of cell volumes. So if we make our box an integer number of unit cells, we can also write this as 1 over n, where you count the number of unit cells that you have in your system. And we want to move this to the infinite lattice. So we take the limit of v to infinite. So our lattice vectors are given by n1 a1 plus n2 a2 plus n3 a3. And the sum over all lattice vectors can also be written as a sum over n1, n2, n3 is 1 up to capital N, capital N, capital N, such that the volume becomes equal to n cubed. So if we now look at this function, let me show you that this indeed is a function of Bloch form. So that this is a function that is periodic in the lattice vector times an e to the I k dot r. And this function is equal to, let me take out an e to the I k dot r, because that's what I want to have in the end for a wave function that is of the form of a Bloch wave function, times square root 1 over v, sum over r, and now we have e to the k dot, and we have small r minus capital R with a minus sign, and omega tau r minus capital R, and we sum over all lattice vectors, so we can shift our sum in the limit of the infinite crystal, which is the limit that we're interested in, e to the I k r times a function u k tau of r, and our function u, which is indeed periodic in the lattice of r, is given by square root 1 over v, the sum over all lattice sides, e to the minus I k dot r minus r, omega tau r minus r. And if I shift r by a lattice vector r prime, then it's just going to be absorbed in the sum, and there is no change in the definition of u, so u is indeed periodic in the lattice. So in this way we can start by a set of local functions and create Bloch wave functions from them and use those as the basis that we use in the crystal calculation. And the local functions we can choose to solve the local problem in a convenient way. Now let's have a look, if we do something like this, what our matrix elements will be between the different basis states. We start with a wave function k prime tau prime Hamiltonian psi k tau. First of all, we know that because these wave functions are of Bloch form, that only wave functions with the same crystal momentum interact with each other. Psi k tau prime h psi k tau. And this matrix element we will call h tau tau prime, which is a function of the crystal momentum. We will not always indicate that it is a function of crystal momentum, but it will be. So our Hamiltonian tau prime is given. Now let's put in the definitions of our wave functions. It's a sum over the lattice vectors, and it's two sums, 1r prime, 1 over v, and then we have an integral e to the minus I k dot r prime omega tau prime r minus r prime, and then the Hamiltonian e to the I k dot r omega tau r minus capital R, and we sum over the volume V. This is the sum over r prime, 1 over v, e to the I, capital K, r minus r prime, and then we can use a bracket notation here, omega tau prime, r minus r prime, h omega tau r minus r. Now let's make a coordinate change. I'm going to say delta r is minus r prime. such that r prime is r plus delta r. And I also know that the sum over all lattice vectors, 1 over the volume, is equal to 1. With this, I have a sum over delta r e to the I k dot delta r from the first, then r omega tau prime r minus delta r h omega tau and r, and the sum over r plus r prime has no coordinate there anymore, so it's a sum of 1 over v, which is exactly 1, so the 1 over v is absorbed in the second sum. This is now our hopping matrix elements tau tau prime delta r, and it tells you how a local state centered around the origin with quantum number tau hops to a state centered around delta r with quantum number tau prime. So an electron can hop from one side to the other by a distance delta r, and it then can change the quantum number that we have. So if these are atomic orbitals, an s orbital can hop to either an s, or an s can hop to a p, or to a d, or to an f, to all different kind of possible local orbitals that we have in our system. The Hamiltonian in this form now becomes a sum over all wave vectors tau tau prime, a sum over all possible hopping distances that we have. Then we have the hopping constant t of delta r going from tau to tau prime e to the minus I k dot delta r, and then the a dagger k tau prime a k tau. So we hop from orbital tau to tau prime, and we have a Fourier transform of the hopping in real space. And what we have here is actually the epsilon k tau tau prime. Now what we have created here is a dual representation. On one hand we have our Bloch waves, and on the other hand we have our local orbitals omega tau. We have a basis in crystal momentum space where we can create a wave function with crystal momentum k and quantum number tau, which can either be the eigenstates or still linear combinations of those. So it's either a band index or a character index that we have. And that wave function is for sure given in a wave function that can be written as a Bloch wave. Sum over r e to the I k dot r omega tau r minus r. We can write it as a sum over all our local functions. And we have also a basis in real space where we can create a wave function with quantum number tau at side r, in which is omega r tau, and this corresponds to the wave function r tau of r, which is by definition omega tau, and now centered around the site capital R. When we do a Fourier transform, we have a plane wave and delta functions, things localized at one coordinate. We now do not have translation symmetry for any vector anymore, but only for a discrete set of lattice vectors. Therefore, instead of momentum, we have crystal momentum. With crystal momentum, we can still create Bloch waves that, when you translate them, pick up the same phase. We can generate these Bloch waves as sums over a set of local wave functions. And we have the dual representations where we have these local wave functions. These are now no longer delta functions, but you have a unit cell which you have to build some basis sets of. So in principle, this could be an orthonormal set that spans all possible functions within exactly one unit cell. That would be a valid definition for the omega taus. You can also have them expand a little bit out of the unit cell, and then you have to, of course, make that you're orthogonal between the different unit cells, and then you can go to atomic-like wave functions. But we have local wave functions that represent two plane waves or Bloch waves in this case, and they are given by a Fourier transform and span a dual basis. We can show this even more when we look at the properties of our creation operators. A creation of a state with wave vector k and quantum number tau. Crystal momentum k is given as 1 over v, the sum over r, and you can read it off here. This is the creation at 0, so we just have that prefactor in there, e to the I k dot r times a dagger r tau. And of course we can then take the Hermitian conjugate, so annihilating a wave function, a Bloch wave function with wave vector k quantum number tau is equal 1 over v sum over all lattice vectors e to the minus I crystal momentum k dot r, and then annihilating that state. And of course we can look at the inverse Fourier transform between them. E dagger r tau is square root 1 over v sum over all crystal lattices e to the minus I k dot r a dagger k tau, and a r for completeness 1 over v sum of k e to the I k dot r a k tau. So we can always move forward, back and forward between crystal momentum space and real space, where real space now are functions with some extent, and you have to have a complete basis set of them to represent all possible functions that you can have within a unit cell. And from that, the Fourier transforms becomes a Bloch wave function, where you have an e to the I k dot r, a plane wave, times a periodic function in the lattice. So now we can look at our Hamiltonian, and we already saw that we have in real space the hopping matrix element, where you move the particle by a lattice vector delta r from orbital tau to orbital tau prime, given as omega tau prime r minus delta r. The Hamiltonian omega tau centered at r, this is a small r, sorry for that. So centered around the origin, you hop by a distance delta tau, by a distance delta r. And we defined epsilon k tau tau prime as the Fourier transform of this sum over all possible delta r's, t delta r tau tau prime e to the minus I k dot delta r. such that in K space it's not an and, the Hamiltonian is given by sum over K tau tau prime epsilon K tau tau prime A dagger K tau prime A K tau. So you have to diagonalize this wave function within the orbital space for each wave vector K, but you're already diagonal within crystal momentum space. In real space we have a very nice understanding of what your Hamiltonian matrix elements mean, but we now still have to sum over all lattice vectors, all distances with which you can hop, tau and tau prime, so we're not diagonal anymore. And we have our t, tau, tau prime, delta r, a dagger r plus, delta r, tau prime, a r tau. You hop from side r to side r plus delta r, going from orbital tau to tau prime. So what we can do is, once we have a system, we can define our local wave functions, which are basically atomic-like. Then you define the hopping matrix elements between them. You have to calculate those matrix elements. Then we make a Fourier transform to K-space, and we're immediately diagonal in crystal momentum. And we now have to diagonalize a small matrix for each crystal momentum that is related to the orbital indices that we have in our system. So we have a crystal with many sides. We hop by a vector which we call delta r, and you hop from orbital tau to a state with orbital tau prime by the lattice vector delta r. And that is your Hamiltonian in real space, and you Fourier transform to get to crystal momentum space. So that's the basic idea of tight binding theory. And what I would like to do in the following lectures is, first of all, have a look at a few examples and see how we can work with this. And once we have done that, I want to go into a bit more detail what actually our local wave functions are these atomic wave functions, and where do we run into problems if you would take purely atomic wave functions. And then introduce also Wannier functions. One of the examples is going to be where I show you how to basically make free electron-like dispersions out of starting with atomic-like wave functions. And we have to talk about how do you hop, well, not only from S to S, but also from S to P or to S to D, and what happens with symmetry, what are the signs of these hopping matrix elements. And just by a few basic considerations on symmetry, you can already understand quite a lot on the different type of band structures. When do you get electron bands, when do you get hole bands. Very good. But that's for the next few videos that we're going to talk about. Thank you very much for your attention. We see each other later.